Have you ever looked at a massive, complex machine and just wondered, how does it know what to do? It all seems so complicated. Well, what if I told you it all starts with something as simple as a drawing? Today, we're going to crack open the engineer's playbook and see exactly how a basic blueprint gets transformed into the automated brain that runs the whole show.
So yeah, that's the big question, isn't it? How can a bunch of lines on a screen possibly contain enough intelligence to command the powerful, precise machinery of an entire factory? Well, the secret lies in a kind of hidden language, a whole system of logic and rules. And don't worry, we're going to break it all down step by step.
All right, so first things first, we need to get on the same page. Think about it. Engineering is global. You've got teams all over the world, speaking totally different languages, who all have to collaborate perfectly. How in the world do they do that? They need one single universal language. And this right here is the key. These technical drawings, they aren't just pictures. They are a full-blown language, built on what you could call coded norms. It's kind of like a shared secret handshake. It's a system that makes sure a design from an engineer in, say, Japan is understood perfectly by another engineer in Germany. There's just no room for error. Okay, so you have a language, but what good is a language if nobody agrees on the grammar, right? It would just be chaos. Well, in engineering, that grammar is a super strict set of standardized rules that govern every single line, symbol, and dimension you see on a blueprint. And these are the rule books that literally prevent that chaos. You see something like ISO 128, that just tells everyone exactly how the drawing should look, so there's zero confusion. Then you have IEC 6617. This one's a big deal. It ensures an electrical symbol means the exact same thing everywhere. I mean, you can imagine how dangerous and expensive it would be if it didn't. And of course, you get regional standards too, like SANS 10111 in South Africa, which fine-tune these global rules for local needs. It's all about creating one single source of truth. So we've got the language, we've got the grammar, the blueprint is perfect, but it's still just a static drawing. How do we make it actually do something? Well, you have to map out its brain, its logic, and the tool for that is the good old flowchart. Now, in this world, a flowchart gets a much cooler name, a logogram. And listen, this is way more than just some boxes and arrows you'd sketch out in a meeting. This is literally the brain of the blueprint. It's not showing you what the parts are, it's showing you what they're supposed to do and when. It's the whole strategic game plan. And this is where it all clicks. You see an electrical drawing like this, you might just think it's a map of wires. But nope. Hidden inside it is a sequence of decisions. It's a simple if-then process, really. If this normally open switch is pressed, then this contactor activates, and then the motor starts. That's simple logic. That's exactly what a logogram is built to capture visually. So we have our visual plan, the logogram. It's beautiful, it's clear, but a machine can't read it. So how do we get a computer to actually understand and execute that plan? This is the critical handoff, where we translate that visual map into code. And that translation is called an algorithmogram. See the connection? Logogram to algorithmogram. This is where the magic happens. It's where the visual design becomes an executable action. It takes that clear, human-readable flowchart and turns it into a coded algorithm, usually using something like Visual Basic, that a computer can actually run. This is the moment the blueprint finally comes alive. This chart breaks it down perfectly. The logogram, that's the what, the beautiful, clear visual plan. The algorithm, that's the how, the hard-working code that actually gets the job done. Think of it this way. The logogram is the architect's drawing. The algorithm is the construction crew's detailed step-by-step instructions. So it's really this crucial two-step process. First, you design the logic visually with a logogram, which makes it easy for us humans to understand it, debate it, and perfect it. Then you translate that perfected logic into an algorithmogram so a computer can execute it flawlessly, thousands of times a second, without ever getting tired. And don't get intimidated by the code. This is what it actually looks like in the real world. This single line of Visual Basic is a complete decision. It's just saying, hey computer, if an error is detected, run the adjust control program. If not, just run the system stable program. That's it. It's an algorithm in its purest form. But these individual algorithms are really just the building blocks. The real power comes when they're all integrated into much larger, far more powerful automated systems that can manage entire projects from start to finish. And the payoff here is huge. You get crystal clear plans. You get automated scheduling that can juggle complex deadlines and dependencies without breaking a sweat. And of course, you have that visual logic we've been talking about. But crucially, this creates a fully auditable workflow. That means every single decision is transparent, traceable, and accountable. No more guesswork.
So, we've gone from drawings to logic to code. But why does all of this actually matter? What's the real-world impact?
If you remember one thing from all this, make it this. This framework makes data actionable. An engineering plan just sitting in a folder is passive information. But by translating its logic into code, that plan becomes an active, intelligent participant in the process. It's the difference between a recipe book and a robot chef that actually cooks the meal for you.
And the applications are just incredibly broad. In industry, this is used for everything from optimizing a factory's production schedule down to the second to troubleshooting complex systems in real time. And in education, especially in vocational programs like South Africa's TVET, it's a total game changer. It allows students to see and understand a workflow visually before they have to write a single line of code, which perfectly bridges that gap between abstract theory and hands-on practice.
And that brings us to a final thought. This whole system is about turning a plan into an automated reality. So if you could take any process in your own work, or even your life, map out its logic, and turn it into code, what would you choose to automate first?